So the continuation of the video, November 2018, paper 1, this is used to the 2024 year 13 PPE. So we've got a reaction here, 2 lots of NO reacting with O2 to give 2 lots of NO2. The substances that are in the rate equation must be either in or before the slow step of the reaction in the mechanism. So which of these is not consistent? So we've basically got to go through all of these, haven't we, to get the right answer. So the first one, in or before. So don't forget the rate equation can only include substances which are actually reactants. So in or before the rate equation, we've got 1 oxygen, an NO, and an NO. So that is consistent. So is consistent with the rate expression. This one, because just make it clear, because NO, there's 2 lots of NO in the rate expression, and there's 1 oxygen in the rate expression. So that one's consistent as well, because you've got 2 of those and 1 of those. This one, I've got 1 NO and 1 oxygen, so it can't be that one. So that's the right answer. Just to confirm it, we'll look at this one as well. This is the rate, this is the slow step. So we've got 1 NO. We ignore the NO3 because that's just an intermediate, another NO, and an O2. So all 3 of those, A, B, and D, are consistent with the rate expression. C is the right answer though. Here's a similar looking reaction, NO2 going to N2 and O2. And you're given a bunch of Ks at different temperatures. So which statement is correct at the highest temperature? The best way to show you how to work this out is, I think, is to actually work out, is to write down what Kc is for this. We've got N2 squared, so N2 raised to its coefficient, and O2 raised to its coefficient, which is 1, which is why I've not written it, and N2O squared. So that's the expression for Kc. And if you go from 838 to 1001 Kelvin, and indeed through all of these, the Kc gets bigger, which means the numerator is getting bigger and the denominator is getting smaller, which means that as you increase the temperature, we're getting more of the products, which means the reaction is favoured, or the forward reaction is favoured as you increase the temperatures. That's the right answer. So it can't have been B, because the opposite would have been true to all the things I just said. At equilibrium, hopefully you know that the rate of the forward and reverse reactions are the same, so it can't have been C. And D is just garbage. The concentration of reactants changes, or both of them increase. That can't be right. Doesn't make any sense. Question 23. Which combination describes a system at equilibrium? Okay, so this one you might remember that if we take a reaction which goes from reactants to products, and we write down a little equation. I'm going to call that G of the reactants and G of the products. Now, as you go through reaction, there is a change in G, which we call delta G, and it's the difference between G of the reactant and G of the products. Let's say it's something like that. Okay, maybe they're very close to each other. I'm going to change it to that. Let's say that they're very similar to each other. So where does the equilibrium lie? Well, it lies in the middle. So what would encourage a reaction to move towards the middle? Why doesn't it go one way or the other? And that's because, whoops, pretty bad picture, never mind, leave it like that. That's because as you go from reactant A and H, simply A going to B, if you've got a combination of A and B together in the reaction pot, that means we've got a higher entropy, we've got a higher S value, so it's either B or C, and that causes delta G to be lower. If you think about it, delta G equals delta H minus T delta S. The higher the entropy, the higher the delta S, if you like, the more negative this value will be. So the answer would be the highest entropy value and the lowest Gibbs free energy value, which is B. Which 2 species act as bronzolary acids? So it's 2 species, must be one reactant and 1 product. So something that's going to lose a proton. I saw someone write on their paper, an acid is something that accepts protons. I think you're getting muddled up with Lewis acids. Lewis acids accept lone pairs, but Bronson and Lowry acids, as you know, let's just think of really simple ones like HCl or HNO3. You know they react by losing H+, right? Right, so which ones lose H+? As you go from there to there, this one loses H+, so H2PO4. It must be either B or D, because that loses a proton. And if you look the other way around, water in the other direction, so that's an acid, that's its conjugate base. This is the base and this is its conjugate acid, so this must lose a proton, which it does. You go from H2O to hydroxide, it's water, so 24 should be D, and it is. Okay. What is the order of increasing pH for the following solutions, the same concentration? This is stuff we've done really recently in the acids topic. So the sodium chloride, I'll write them over here to make it really clear. So sodium chloride is a neutral salt, so it'll be pH 7. Ammonium chloride is an acidic salt, so ammonium can release H+, so it'll have a solution of that will have a pH less than 7. Carbonate ions are basics, they're going to be greater than 7. And you've got the conjugate base of ethanoic acid, so CH3COO-, which is also going to be greater than 7. But a carbonate ion is more basic than the conjugate base of ethanoic acid. So we could say that this one has got it's not way bigger than 7, but it's going to be more than this one here. So the order is, that's the lowest pH, then that one, then that one, and then that one. So hopefully this matches up with what the answer is, which is C, I'm saying, and 25 is C. That's the right answer. So the tricky thing there, I suppose, you should absolutely have known that, and that these are basic. The tricky one is which of these is the most basic. But this is a 2- ion, that's a big enough clue. 2- ion going to accept a proton more easily than a 1- ion, I suppose. That's probably the easiest thing to think about. So a Lewis base is something that's got a lone pair that can be given away to a Lewis acid. So which one's got a lone pair that's free? Simply, if you draw them all out, you'll see this is, of course, we've got 3 lone pairs, 2 lone pairs, 1 lone pair. No lone pair, so 26 should be B, which it is. Indicator has got a pKa of 5.1. So, to just remind you, an indicator is a weak acid and it's got a pKa associated with it. So you typically want to use it, the colour change will happen around a pH around about 5, or a unit either side of 5. So if we just think about this bit by bit, so colour, so pK in is 5.1, and therefore, okay, just pause it to give yourself a chance to think about how to answer this. This is quite a challenging question, I think. Let's start with the answer. So the answer is A. So well done if you got it right. Think about what's going on here. If you've got a pKa of 5.1, it means that the pH at which the colour change would happen is around about 5.1. So at pH 7, so that's kind of the pH for weak acid, right? At pH 7, you're more alkaline than that kind of intermediate, or the pH where they're about balanced. So at pH 7, you're more alkaline. So more alkaline means you're going to be towards the right hand side, because you're going to, in an alkaline situation, you're going to deprotonate this acid. You're going to end up with the products in that situation. It's the best way I can argue it. So you're going to be on that side, and you're going to get colour B. Let's go through the others though. So at pH 3, which is a more acidic situation than the pKa, or the pH at which it would change colour, that's more acidic, so that's going to drag you this way. That's going to force the equilibrium in this position in this direction. So it ain't that one, because that would give you colour A. At pH 7, the concentrations of those will be the same. Now that would be true at pH 5.1, so it ain't that one. And at pH 3, so under those acidic conditions again, you'd expect to get the HN. HN is a more significant or high concentration. So you've got these the wrong way around. That would be that way round. Yeah, not an easy question, I think. Question 28, which is correct for the reaction. So let's work it through. The oxidation numbers you should be able to do quite straightforwardly. That's the element P, which is therefore 0. In water, each oxygen, well, the oxygen is -2 and each hydrogen is +1. That's also true in hydroxide. +2 and -1. And just to check, these two add together to give the 1-, which is what hydroxide is. In pH 3, H is +1, as always, except in a hydride, and so the P must be -3. And in this we've got the oxygens are -2, the hydrogens are each +1, and so the phosphorus there is, the phosphorus must be +3 to check that makes sense. So +1, +2, +3, 4, 5. Got that wrong, haven't I? It's +1. Would you check that's right? So +1, 2 for each hydrogen, +3 for the phosphorus, -2 comes to -1, and that's the charge of that thing. So P there is +1, and that makes sense because we're going from P4, and that's gone down to 3-, and so 3 electrons have been given to that one phosphorus, if you like. So they must have, the other 3 phosphoruses must each have lost 1 electron, if you think of it in those terms. Okay, so the P4 is both the oxidizing and reducing agent there, so it must be D. Just going to check that. It is right, it's D, which describes the flow in a voltaic cell. I'd save a bit of time. I've just quickly drawn a voltaic cell. You become very familiar with these, very comfortable with drawing these. You need to be able to draw these from memory. You need to know that on the left hand side, you get oxidation going on. If it's been set up properly and you get a positive voltage, that is, you have the negative electrode, or where the oxidation is taking place, on the left hand side. On the right hand side, you'd put the more positive electrode where the reduction is taking place. An example would be zinc going to zinc 2+ on the left, oxidation, the more reactive metal on the left, less reactive on the right. Copper 2+ ions getting reduced to copper. So oxidation, ox-red, oxidation on the left. Anode, is where oxidation takes place. The clue is that O is in the middle of the word, and cathode is where reduction takes place. So electrons are flowing around the circuit in this direction. And just remind you now that negative anions are flowing around the salt bridge, kind of in a clockwise direction, the opposite direction to the electrons, and positive ions are going from left to right as well. So let's go through these. From the flow of electrons it's asking about, from the cathode to the anode, well that ain't right. From the anode to the cathode, well that is right. Through the external circuit, through the wires, well that is right. So that is the answer. From the oxidizing agent to the reducing agent, it's saying through the salt bridge, well the electrons don't go through the salt bridge. Electrons don't go through the salt bridge. It's neither of those two. That's that one. Question 30. Question 30, which is correct for redox reaction. We haven't done this question, where the standard electrode potential is negative. So you're just plugging numbers into here. So if E is negative, delta G must be positive. So it either had to be C or D. Even if you've not done this question, you're just going to plug the numbers in. And if delta G is positive, you could work out as well, can't you, that K must be less than 1, you can either try and think about it mathematically, and imagining what natural log of K would be if it's much bigger than or much smaller than 1. But I think simply easier than that is, that if a K is greater than 1, it's the equilibrium's far to the right, it's a favoured forward reaction, and if Kc is less than 1, it's the backward reaction that's preferred, and it's a reaction where the reactants are favoured, so the backward reaction is favoured. And so we've got a delta G is positive here, which we've just worked out, and if delta G is positive, that means K is less than 1, so that has to be the answer. Because delta G being positive means the backward reaction is favoured, which is the same as K being less than 1. Right, so it's that. You don't have to do any kind of maths there.